Hello, students. Had a couple more come in from section 4.2. The questions were 7, 8, 9, and 17. So I did 7 and 9 in the other video, so I'm going to leave those alone. I'll take a look at 8, and then it said 17. So let me check and see. 17 is the baseball card one. Okay, so I did that for the last video. So check the last video if you're interested in that. This one's going to be mainly focused on question number 8, which is one of the theorems that we've had the chance to work with. So let's give a little extra space here. So when you are working with these theorems, I think the piece to think about is the fundamental theorem of arithmetic says that you can write the prime factorization of a number exactly one way if you put the primes kind of in order from smallest to greatest. So the idea is if someone had the number 36 and you factored it down as 4 times 9 and then 2 times 2 and 3 times 3, but I didn't do that. If I did this as 12 times 3, that I could still break this down and end up with a prime factorization of 2 squared times 3 squared, whereas you would get a prime factorization of 2 squared times 3 squared. So I want to make sure that it's clear. It's actually, we're talking about something that is equivalent up to what we call ordering. So again, if someone had written 3 squared times 2 squared, we don't want to think that that's a different grouping of primes than 2 squared, 3 squared. These are, in fact, completely equal. What we are saying is that if your number, when you did your prime factorization and you got 2 to the 7th as something in your number, and I ended up only with 2 to the 5 in my number, we would be able to say those multiplied by some other thing, and it doesn't even matter what the other thing is, but we would be able to say, I'm sorry, that's it. If you've got all your 2's in front, and one of them is 2 to the 5th and the other is 2 to the 7th, these numbers are not equal. So part A says, if we know 4 divides n, and we know 9 divides n, can you prove that 36 must divide n? So as you go through and do that, we'll start by saying we can assume that these two are true. Okay. It's got an and statement, both have to be true. So now 4 divides n, that means that n must be equal to 4 times some number. And I'm going to call that number k in this situation. Okay. And I also know that 9 divides n. So that means n is equal to 9 times some number, where that number, again, is some whole number, a unique whole number. Well, now, if you look at this, n has 4 and the other n has a 9 here, so n is actually equal to 2 squared times k, but n is simultaneously equal to 3 squared times j. And well, I don't know a whole lot, but if these two are equal, right, then 2 squared times k has to divide n. But n is 3 squared times j. So I have 2 squared times k divides 3 squared times j. And that means that 3 squared times j has to equal 2 squared times k multiplied by some whole number to make that work out. And I could choose any whole number. Make sure it's not a variable you've chosen before so we don't kind of get too jumbled up. And so over here on the right-hand side, I have a factorization that includes a 2 squared. I don't see a 2 squared on the left-hand side, which means that 2 squared must divide j. And that's because in order for these to be equal, if 2 squared is on the right-hand side, so it divides the right-hand side, it has to divide the left-hand side. And if 2 squared divides j, what it's telling you is that n is actually equal to like up here, this is 3 squared times j, but j, oops, I should say j equals. J has to be equal to 2 squared times some whole number. I don't know what that whole number is. I've already used k and j, so why don't I choose and n? Why don't I choose x? Okay. So j is equal to 2 squared times x, and again, x is some whole number. So 3 squared times 2 squared times x is what I can substitute in here. And that means n is equal to 3 squared times 2 squared times x. And that tells you that n has to be equal to, if you look at it, 3 squared is 9, 2 squared is 4, is equal to 36 times x, which means 36 has to divide n. So that is how you can show that if you know that 4 works and you know that 9 works, then 36 has to work because they don't have any factors in common. Yeah, it doesn't simplify quite that way. Yeah, it looks like part B is very, very similar. It just doesn't have perfect squares, but that's doesn't matter. It really doesn't matter. It's the exact same argument. Now you're just saying, what do I do with 12? So now 12 has to divide n, whatever n is, which means n has to be some multiple of 12, but it also has to be a multiple of 35, and 35 is just 5 times 7. So I know it has to include all of those factors, which would include a 2 squared and a 35. 2 squared times 3 and a 35. That gives you the 12 and the 35 there. All right. Okay. Well, those are the big ones for now that took care of number 8. Hopefully that gives you a push in the right direction if you didn't have one already. And that's it for now. I think that's going to do it. All right. Off you go.